Welcome to our presentation in which we show you how you can use surrogate models to improve the test generation in Android. We're gonna show you now a quick demonstration of Mate and highlight the issues of Android test generation. Note that we are within the execution of a genetic algorithm. In particular, Mate restarts the app under test next, followed by the actual test execution. As you have observed, the time for restarting the app under test can take up several seconds. In Mate, the restart operation roughly takes 6 to 10 seconds, while other tools, like SwiftHand, require up to 30 seconds for the same operation. That's a lot, and constitutes one of the issues in Android test generation. Restarting the app under test is an expensive task. Another issue is the execution time of individual actions. We could observe that certain actions took longer and others were quite quick. The execution time in Mate varies between a couple of milliseconds up to roughly 1 second. This all depends on which framework you use to execute the actions and whether timeouts are defined between two consecutive actions. But in general, we can say that the execution time constitutes a major time-consuming task. Before we describe the surrogate model, let's briefly review the structure of a genetic algorithm and the test execution in Android. We start with an initial population, typically randomly generated. In order to evaluate the fitness of the individuals, we first need to execute them on the emulator. Then we can derive the fitness value, perform selection, crossover and mutation. This process is repeated until a stopping criterion is met and the optimal solution is returned as a result. Now to the test execution process. We initialize a new test case and iteratively fill the test case with actions until a maximum number of actions is reached. That means we select an action, update the test case accordingly, execute the action on the device, and update the current state. After the test case has been completed, we perform some post-processing steps like serializing the test case to replay them on demand. Lastly, we restart the app under test to provide a clean starting state for the next test case. Now we can introduce the surrogate model. In fact, it's a simple extension of a traditional GUI-based model used in Android testing. A vertex is simply a state abstraction, and an edge consists of a source and target state, as well as an action and a set of traces. The traces serves as input for the fitness evaluation. The objective of the surrogate model is the prediction of the outcome of actions, that is, the set of traces and the resulting target state. By doing so, we can save the costly execution of actions. Here we have a very simple example of such a model, consisting of three states, S0, S1, S2, and two edges connecting those states. We can move from S0 to S1 with a click action, and likewise we can move from S1 to S2 with a swipe action. Both actions are producing different set of traces. The cool thing is that we do not need to adapt the genetic algorithm itself, but solely the test execution process in order to incorporate the surrogate model. Here we can see again the test execution process, where in red are highlighted the necessary changes for the surrogate model. Every time we select an action and update the test case, we need to query the surrogate model whether we can predict the action. If we can, we cache the action, update the current state, and proceed with the next action. If we cannot predict the action because the action is new, for instance, we need to execute the cached actions in order to bring the app under test in the correct state. Then we execute the selected action and update the surrogate model with the new information. The more actions we can predict, the more time we can save for additional exploration. If we could predict all actions of a test case, we can save the costly restart operation. Now let's move on to the preciseness of the surrogate model by going through an example. Here we can see a couple of states of an app called Money Wallet. We can reach a particular state by following the action transitions. If we click on first time, we reach the state in the middle. Swiping left brings us to the next state. If we click on the check mark, we come to a new activity in which we can create a new wallet. We can fill out the form and click on the check mark, and this brings us to a new state showing a list of transactions which is empty initially. Recall from the definition of the surrogate model that a vertex represents a state abstraction. Depending on the chosen abstraction level, the surrogate model reflects a more or less accurate model. We have evaluated the following three state abstraction levels. The first abstraction level which we call activity name abstraction, we consider two states to be equivalent if they refer to the same activity. This leads to the following results. We have four states, S0 to S3, where S3 consists of three views because they refer to the same activity. In the widget composition abstraction, we consider two states to be equal if they refer to the same activity and have the same widget hierarchy. This leads to five states, S0 to S4, where state S4 has a distinct widget hierarchy than state S3. In the last abstraction level, which we call widget content abstraction, we consider two states to be equal if they not only refer to the same activity and have the same widget hierarchy, but also have the same text inputs and content descriptions. This leads to six states, S0 to S5, where S4 is different from S3 because the text inputs are distinct. There are a couple of problems related to the usage of surrogate models, but also to traditional model-based testing. First of all, one may observe non-deterministic actions, as illustrated in the example. To overcome this issue, we associate with each transition a frequency counter that tells us how often the action has been triggered so far. Here, the click on first time leads to two distinct states, but in favor for the state shown on top. Whenever we need to predict such an action, we take the transition with the highest frequency counter. Another problem is illustrated in the following example. We may leave the app under test by crashing the app or pressing back on the main activity. This may happen during the execution of cached actions. In both cases, the only option is to abort the test execution for the current test case and proceed with the next one. Lastly, we may encounter a non-applicable action during the execution of cached actions. As illustrated in the example, we see two states where on the left the list of items contains the category others, which is missing on the right side. We may now need to execute a click on the list item others, but we can't. In such a case, we simply pick a random action applicable in the current state. Now we come to the evaluation part. We asked ourselves the following three research questions. RQ1. Does the state equivalence level, that is the abstraction level, influence the effectiveness in terms of number of test cases and coverage? That means, does a more fine-grained or less fine-grained surrogate model has a positive or negative impact on the test execution? RQ2. Can the surrogate model avoid costly restart operations? That means, can we fully predict individual test cases to avoid the restart? RQ3. Does the use of the surrogate model increase the number of tests and coverage? That means, can we generate more tests by saving costly restarts and the execution of individual actions, and use the additional search budget to explore more parts of the app under test? We conducted the experiments on 10 open source apps that we used in previous studies. The results are as follows. Here we can observe a different picture. We measured both activity and basic block coverage for the three abstraction levels. In both cases, the activity name abstraction leads to poor results, in contrast to the more fine-grained surrogate models. We can conclude that a less accurate surrogate model leads to more tests but less coverage, while a more fine-grained model leads to less tests but a higher coverage. In order to determine which is the best trade-off, we performed a tournament ranking that works as follows. We compared the different abstraction levels pairwise and gave a point to a configuration if there is a statistical significance in terms of tests or coverage, that is a p-value less than 0.05, and the Varga-Delaney effect size is greater than 0.5. While the activity name abstraction outperforms the other configurations in terms of tests, the more fine-grained surrogate model configurations dominate in coverage. Since we aim for a configuration that maximizes coverage, we consider the widget content abstraction as the best trade-off. To answer RQ2, we measured the number of executed restarts and the rate of saved restarts. On the left diagram, we can observe that the activity name abstraction performs the fewest restarts, which corresponds to a rate of 97% restarts that could be saved, as shown on the right diagram. While the number of executed restarts is a couple of times higher for the more fine-grained surrogate models, the rate of saved restarts is above 70%, meaning that we can save a vast part of restarts even with the more fine-grained configurations. Now, the probably most exciting question. Is the best surrogate model configuration better than the configuration without a surrogate model? We measured the number of tests for both configurations as shown in the diagram. The surrogate model configuration produces twice the number of tests, 775 in contrast to 342. Regarding coverage, we can observe that the surrogate model configuration is also slightly better in both activity coverage 71% to 69% and basic block coverage 51 to 48%. In total, there is a favor for using the surrogate model in Android test generation. There are a couple of points we'd like to address in the future. First of all, we would like to evaluate the entire study on a larger set of apps. We know that 10 apps are not very representative. Next, there might be different or even better strategies for non-deterministic actions. Instead of picking the transition with the highest frequency counter, we could use a threshold or pick the transition that includes the largest set of traces. Lastly, we would like to incorporate a further abstraction level, namely cosine similarity, which leads to an even more fine-grained or accurate model and hopefully helps in improving coverage. Let's end the presentation with a few conclusions. We observed that a more fine-grained surrogate model leads to less tests but a higher coverage, while a less fine-grained surrogate model leads to more tests but less coverage. In any case, a surrogate model can save costly restart operations, can execute more tests, and can achieve higher coverage.